Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good morning, guys. Okay, how are you guys?
Alhamdulillah sihat sir.
Okay, bagus. Okay, ready
Okay,
eh?
okay.
Alright, so you can get my slide here. Can you see my slide?
Yes, yes.
Boleh, sir.
Alright.
Boleh, sir.
Boleh.
So let's start our lecture today. So we continue on the topic number 1. There's the introduction to instrumentation and measurements. Alright. So today we study about the performance characteristic and also the type of error. Okay. So the performance characteristic, you can see this one, the performance characteristic that show the performance of instrument lah. For example, like accuracy, precision, resolution, and sensitivity lah. Okay. So the performance characteristic allow the user to select the most suitable instrument for the specific measuring job lah. For example, if you want to measure the voltage, okay, measure the current, we can use the uh, multimeter, okay, digital multimeter. Also, you can also use the analog multimeter, depends lah. If you are familiar with digital, okay, you can use the digital. If you're familiar with the analog, you can use the analog, okay. But you have to know the performance of the instrumentation, the measurement device, okay. So for example, you have to study about the accuracy using the digital, okay, multimeter, and the precision and so on, okay. So we have two type of basic characteristic. We call the statics and dynamics. All right. So you can see this one. Static is the measure the constant process condition. Okay. That means the process will be static lah. Will be statics, and then the dynamic we are measuring in the varying process condition lah. For example, like this one. Okay. So we measure the battery. Okay, the battery cell. So this is static measuring lah. So this one no dynamics. Okay, this is statics. Okay, we just from this cell we use our digital multimeter and then measure the voltage here. So this is called the static. Okay, static measurement or constant process condition lah. And then if the dynamic, for example, the our watch, okay, our smartwatch measure the heartbeat, for example, measure the heartbeat, okay. So that is dynamic when we are running. So how our for example, like smartwatch measure the heartbeat lah. That is the process of dynamic process to measure our, for example, like heartbeats, okay, or for example to measure the current our currents, okay. So current in the, for example, is still in the varying process. So when we measure the current, so maybe you get the dynamics characteristic lah. Alright. So on the static characteristic, we have to study about the accuracy. Okay, so the accuracy is the degree, the exactness or closeness of the measurement compared than expected value. For example, yesterday that I mentioned to you, okay, this battery is the expected value is the 14.8 volts. Okay, 14.8 volts. And then when we measure using the digital multimeter, we got 15, for example, this one. All right, so the exact value for this battery is 14.8. Okay, 0.8 volts. And then we are use the digital multimeter. So we got 15.0, for example, 0.8 volts. Okay, so here we can get the error lah. The error for this measurement. That means the expected value 14.8 divide minus by 15.08. Okay, 15.08 right? So you can use your calculator, right? 14.8 minus 15.08. So the error will be, okay, 0.28, okay, 0.28. Oh, sorry. Okay, 0.28 lah. Alright, this is the error, the error. So you want to calculate the accuracy, so you have to use this formula lah. 1 minus expected value minus by measure value divide by expected value lah. Okay, this is formula to calculate the accuracy lah. Okay, for example, like this one, so 0.28, okay, divide by 14.8, all right, and then multiply by 100. Okay, so the percentage of error we got 1.89%. Okay, this is the percentage of error lah. So to get the accuracy, so 1 minus 1.8. Sorry, I use my mouse, not. Okay, so 1 minus 1 point. Sorry, this one is 100. 100. Okay, sorry, not 1. This is 100. All right. Okay, 100 minus by 1.8. Okay, so the accuracy is 98.1. Okay, so this example, yesterday we measured our expected value for this voltage battery. Okay, is 14.8 volts, and then we measure using the digital multimeter. We got 15.08. Okay, so from this we can get the error. Okay, our error will be 0.28 volts plus minus 0.28 volts, and then using this one, 0.28 divided by 14.8 multiply by 100, you got this percentage, error percentage, and then to calculate the accuracy, okay, the accuracy is hundreds minus by percentage of error lah. So that's why we got the this is for accuracy in percentage. That's why 98.1%. All right, this is for calculate the accuracy. Okay, next calculate to precision. Okay, next characteristic for the static characteristic is the precision lah. Precision is the measure of consistency or repeatability of measurement. All right, for example, like successive reading do not differ. Okay, you can see this figure here. Okay, this we call low precision. Okay, low precision. For example, we use the digital multimeter. Okay, we use the digital multimeter measure the battery. Okay, the measure is 15.08. Sorry. Okay, our measure is 15.08. Okay, this is for example like first measurement. Okay, second measurement. Okay, we got 15.07. Okay, and then third measurement using the determinator we got 15. This some example 0.6. And then for measurement we got 15.08. Okay, for example, this is some example. This one we call the high precision. Okay, high precision, but it's a low accuracy lah because our expected result will be 14.8. 15. But this one will be consistency. Okay, that means every measurement will be almost similar. Okay, almost similar. When we use the multimeter, so we do a lot of measurement, but the consistency of the output will be almost similar lah. For example, like this, 0.6, 0.8, 0.7, and again. Okay, that's we call the precision lah. Okay, for example, like this one, this one is low precision. Okay, because you can see this one, this one, and another one is okay, not close. Okay, not close. All right, but this one is the we can call as the higher accuracy lah. Okay, because this, for example, this is our expected this is our expected output here at the middle. All right, so all the point here, the measure is almost to the expected result. This one will be higher accuracy lah, but the precision will be lower. All right, for example, like this one low precision and low accuracy lah, because this is our expected result. For example, our expected result here. So all the measurement will be far to the expected result and not close each other, not close each other. For example, this one and this one not close. So this one we call the low precision and low accuracy lah. Okay, compare this one, okay, close with the exact value, and then every reading will be almost close. So this one we will call a higher precision and higher accuracy lah. Okay, this one, so for our measurement, normally we want like this, okay, higher precision and higher accuracy. Okay, compare this one with the higher precision. Okay, this one, high precision, but it's a lower accuracy lah, because our expected result, expected output here should be here. So all the output far from the expected. So this one we call the low accuracy, but the efficiency is very high. Okay, that's its comparison between the accuracy and the precision. Okay, so this is how to calculate the precision. 1 minus value of the n measurement divided by average set of measurement. Minus by average set of measurement divided by average set of measurement. Right, this is formula for calculate the precision. Okay, 1 minus, okay, this one will be absolute, absolute. So if you got the negative, so automatically will be positive lah. Okay, this one should be in the positive, that's why you put absolute here. All right, this one we will call the absolute. So if your data you got negative, some negative value, so automatically will be positive. Okay, should be in positive. All right. So the formula will be 1 minus value of n measurement minus average set of measurement divided by average set of measurement. Okay, this is to calculate the precision. Okay, next characteristic of the static characteristic is the resolution. Okay, resolution is the smallest change in the measurement variable to which an instrument will be responded. For example, like you can see before this, I measure using the using the digital multimeter. So our output will be 15.08. Okay, this is our resolution lah. So maybe you can set if the good is a small resolution lah. For example, 0.0765. Okay, for example, like this. Okay, this is we call the resolution lah. Okay, the smallest change in the measurement measurement variables. This one we call the resolution. Okay, and then next characteristic is the sensitivity lah. Sensitivity is the ratio of change in the output response of the measurement to the change of the input or measured variable lah. Okay, so another characteristic is the expected value. Okay, this is based on the maybe on the manufacturer value, okay, what we expect from our device, for example, like our battery. So this one from manufacturer, they give a exact value, okay, already tested. For example, like 14.8, this is the rated value for this battery, all right, for example, like from manufacturer. Okay, and the error, okay, the error, the deviation of the true value from the desired value lah, okay, that I mentioned to you. So from this one, this exact value is the 14.8, but we use the digital multimeter, we got 15.08 volt lah. That's the difference between the exact value and the desired value. We call the error. Okay, we call the error. Okay, so next is the error in measurement. Okay, when you do the measurement, always introduce the error lah, always. Okay, always. That's why I showed you yesterday. So when we measure the battery, so from the expected result, we suppose get the 14.8 volts. Okay, 14.8 volt, and then we use the digital multimeter, we got 15.08 volts. So the, if you try another, so maybe we can get 15.07, for example. So that's why will be introduced, every measurement will be introduced the error lah. Okay, it's very difficult to define the true value. True value, there is the always different. Okay, actually the true value, for example here, based on the manufacturer lah, for example like our battery here, for the manufacturer already test and then do some experiment, and then they are consider this this battery cell will be produce 14.8 volts. Okay, that set by manufacturer lah, set by manufacturer is a 14.8 volts, for example. Okay, so error can be expressed either the absolutes or percentage of error. Okay, absolute will be in positive lah. For example, the absolute error, this is formula for absolute error. Okay, expected result minus by measured value lah. Okay, for example, like our battery 14.8 volt minus by 15.08. Okay, the output will be negative 0.28, but there is absolute error, so will be positive lah, 0.28. Okay, the error will be 0.28. Okay, and then we have to calculate the percentage of error. Okay, this is formula, formula for calculate the percentage of error. Expected result minus measured value, then divide by measured value lah. Okay, then multiply by 100. Okay, okay, so this is some example. Okay, so given the expected voltage value across the resistor is 80 volts. Okay, the measurement is 79 volts. Okay, first you have to calculate the absolute error, and then calculate the percentage of error, then relative accuracy, then the percentage of accuracy. Okay, I give you 5 minutes, okay, to try this one. Okay, maybe we can try same together. We can try together lah. Okay, for example, our the absolute error here will be the expected is the 40 volt. Sorry, 40, 80 volts here minus by 79 volt. Okay, so will be negative 1 lah. So because this is absolute error, okay, will be 1 1 volt. Okay, the error will be 1 volt. And then you have to calculate the percentage of error. Okay, percentage of error 1. Okay, divide, okay, 1 divided by 80. Okay, multiply by 100. 1 divided by 80 multiply by 100. Okay, the answer is 1 divided by 80. This is expected. Voltage multiplied by 100, 100 acres. Okay, so the answer is 1.25. Okay, 25%. All right. So, okay, to calculate the percentage of error here, actually, is 100 minus 1.25. Okay, 1 minus 25%. Okay, 100 minus by 1.25. So 98.75. Okay, percent. Okay, so and then to calculate the relative accuracy, so this percentage divide by 100 lah. Okay, that means 98.75 divide by 100. Okay, so the answer is 0.9875 lah. Right, the answer is 0.9875. Okay, so this is an example. Okay, so there is a solution lah. Okay, you can see, check the answer. Okay, right. So next, maybe you can try another one lah. Okay, this one. Okay, from this example, from this value given by table 1.1, calculate the precision of the sixth measurement. Sixth measurement here lah. Okay, so, okay, the sixth measurement is 100. All right. So you have to calculate the precision lah. That means first you have to calculate the average of this value lah. The average of this value. All right. The average. For example, you calculate from 1998. Okay. Plus 101 plus 102 and divide by 10 lah. Divide by 10, you get the average value for this. Okay, for this Xn. Okay, and then the answer will be average value divide by the n measurement. Okay, for example, here will be 6 measurement divide by average value. Okay, that is the precision lah. All right. Okay, for example, like this one. So first you have to calculate the average measurement value. Okay, 98 plus 101 plus and so on. Okay, divide by 10 because of we have 10 reading, and then the answer will be 100.5. Okay, 100.5, and then the precision for 6 reading will be 100 divided by 100.5. Sorry, 100 minus 100.5 divided by 100.5. Okay. So this is the precision, but in the percentage, okay, you have to multiply by 100 lah here. So the precision of this the 6 reading will be 99.5 lah. Okay. So the percentage is 99.5. Okay, in percentage. Okay, all right. So maybe we can try this one. For example, like this one. Okay, so the expected result here. Okay, we give you 5 minutes to try this one. For example, the expected result. This one we can call expected result. Okay, is 100 lah. Okay, 100. Expected result will be 100, and then you have to calculate the accuracy. Okay, the accuracy here. For example, this accuracy. Okay, calculate the accuracy. For example, the accuracy for first measurement is the 98. 98. Okay, the accuracy 98% lah. Okay, you can calculate. Okay, for second measurement will be 99, 99%. Okay, in percentage. Okay, and then third measurement will be 98, 98%, 97, okay, 97%, 99, okay, 100% accuracy, 100% accuracy, okay, 97, okay, percent, 98%, okay, this one will be 94, 94% for accuracy, and last one will be 99 lah. Okay, for example, our expected, okay, our expected output will be 100 lah, will be 100 So that's why here, for example, the expected 100 minus by 98 divide by 100. So we got, this error will be 2%, and then 2%, okay, 100 divide minus by 2%, we got 98, okay, 98% lah. Okay, for example, like second measurement, okay, 100, okay, minus by 101, okay, we got negative 1, divide by 100, we got 19, negative, actually negative, but this error will be absolute, absolute. Negative 1 will be 1 lah. Okay, will be 1. Okay, so multiply by will be 1, and then 1 minus 100 by 100 minus by 1. Okay, that's why the percentage of accuracy will be 99 lah. Okay, here for second measurement. Similar like third measurement. Third measurement is the 98, okay, 98%. Okay, so 100 minus 102, okay, we got negative 2, divide by 100, okay, we got negative 2, because this is absolute error, so will be 2 lah. 100 divide by minus by 2, so the output will be 98. Okay, the percentage of accuracy lah, so percentage of accuracy will be 98. Okay, here. Okay, so next is the type of error. Type of error, here we have three type of error. So the first is the gross error. Okay, sometimes we can call as the human error. All right, and then second error, we have a systematic error. On the systematic error, we have either the static error or dynamic error. Okay, from static error, maybe it can produce from the instrument error or human error, or observation error, and so on lah. And then last is the random error. Okay, random error. Okay, and then next we go one by one. Okay, the gross error lah that I mentioned to you. Sometimes we call the human error lah, because this error caused by human mistake in reading, or mistake on the using instrument lah. Okay, using the instruments. Okay, may also occur due to incorrect adjustment of the measurement and the computational mistake lah. Okay, so this one cannot treated by mathematicals. Okay, and then also cannot eliminate, but can be minimized. Okay, make sure we use the proper instrument lah. We use the proper instrument. Okay, so for example, improper use of the instrument, this reading can be minimized by taking proper care in reading and recording measurement parameter lah. Okay, for example, in general, indicating the instrument change ambient condition to some extent when connected to the complete circuit lah. Okay, therefore several reading at 3 reading must be taken to minimize the effect of ambient condition change lah. Okay, this sometimes we call the gross error. Gross error, some of the book refer to the human error lah. So human error maybe on the mistake on the reading. Okay, that's why when we have to take more than one reading lah, more than one measurement. Okay, next is the systematic error. Okay, systematic error is due to shortcoming of the instrument. Okay, such as defective or worn part, aging of effect of the environmental of the instrument. So sometimes of the, for example, like mechanical part, they have the lifetime. Okay, they have lifetime, like a spring. Okay, like a contact. So they have the have the lifetime. So maybe on the 1000 for example, like contact. So 1,000 contacts, so the effect of the measurement will be effect, for example. That's why we have to know lah. That is we call the systematic error based on the instrument itself. Okay. So inside the instrument, maybe we have the mechanical part, okay, the electrical part, electronic part, okay. That's why one of the factor is the defect on the part, okay, the component inside the instrument or the aging, okay, the lifetime, the cycle of the mechanical part, for example. Okay. So in the systematic error can be subdivided into two. There's a static and dynamic error. Okay, that I mentioned to you. Okay, so the statics caused by limitation of the measurement device or physical law governing its behavior. Okay, and then for the dynamic caused by instrument not responding very fast to follow the change of measured variable lah. For example, dynamic kan. For example, like our smartwatch to measure the heartbeat. Okay, so when we are running, so it quite tough to get the static value. Okay, static value. That's why we call the dynamic lah. Maybe you can the data, the measurement will be fluctuated. Okay, very dynamic lah. Maybe 98, okay, 94 or 101, for example. Okay, using the smartwatch. That's why it's we call the dynamic error lah. Okay, because our instrument not respond very fast enough lah to measure the.
Sir, tak dengar.
Sir tak dengar, sir.
Okey, dengar tak?
Okey, baru dengar.
Tak dengar.
Saya termute.
Tadi tak dengar.
Alright, tadi. Okay,
siap.
Oh ya, it's okay.
so, okay, saya back to this one boleh? This one
Okey, boleh.
Okay,
Alright,
thank
so
you.
this one, So, sorry forgot to unmute, alright? So, type of systematic error, we have three type of systematic error. This one we call the instrumental error, okay? And then we have the environmental error, and also we have the last for the systematic error, we have the observation error lah. Right, we go one by one. The instrumental error, okay, that I mentioned to you, instrumental error is based on the instrument itself lah, inside the instrument. For example, inside this digital multimeter, okay. So inside this one lah, so the component inside this one, for example, like okay, the irregular spring tension, scratching of spring inside this one, maybe we have the mechanical part. So mechanical part, maybe we have the life cycle lah. Maksud that mean maybe one, for example, like contact our switch, okay, switch on the, okay, to switch on the lamp. All right, for example, this already test for uh, 1 million cycle. That's mean, okay, after 1 million, so maybe it will be broken, so you have to change new one lah. Okay, that is the mechanical part lah. This one we call the instrumental error lah. We have to change with new one. Okay, so this error actually we can avoid by selecting the suitable instrument, okay, for the particular measurement application, or also can change the new one, the new instrument, the new instrument to do a measurement. All right, and then second, apply the correction factor by determining instrumental error. If you know this instrumental error, we can apply the correction factor lah. But if we cannot measure the instrumental error, so maybe we can change to new instrument lah. Okay, and then number 3, we can calibrate. Okay, we can calibrate the instruments against the standard. For example, like our oscilloscope. Okay, so the first thing when we are do measurement, before we do the measurement, first we have to calibrate. Okay, we have to calibrate our instruments, and then after calibrate, okay, then we can use the, okay, the oscilloscope lah. Okay, if for example, if you do calibration, so you don't get the good calibration for your instrument, you have to return back to the manufacturer. Then manufacturer will be calibrate again lah for you. Okay, so this, okay, next will be environmental error. Okay, environmental error is the due external condition affecting the measurement, including the surrounding area, okay, such as a change in the temperature, humidity, barometer pressure, and so on lah. Okay, for example, like when we measure this one, we call the anemometer that I mentioned to you yesterday. So this one will be measure the speed, okay, the wind speed. Okay, the wind speed will be changed, depends on the weather, weather. Okay, that means this also we can call as the environmental error lah. Okay, so this one can be avoided. Okay, use the air conditioner. Okay, that means maybe can use the vacuum rooms. Okay, not air. For example, we can do some measurement. Okay, we have the fan. Okay, the fan will be affect the reading, for example lah, and then we have to use the aircon. Okay, to reduce the fan. Okay, the winds. Okay, on your measurement lah. Okay, and then second, sealing certain component in the instrument. Okay, and also use the magnetic shield lah. If when do measurement, you have some magnetic fields inside your working area, so we have to use the magnetic field lah, magnetic shield, okay, to protect our instrument. And then observation error. So observation error actually is based on the observer, okay, based on human actually. Okay, so we sometimes we call the parallel error, okay, and estimation error lah. So we're reading the scale. For example, like normally it happen when we are reading on the analogs, okay, analogs instrument lah. For example, like our they use the, for example, use the ammeter or decimeter, okay. So if the using the analog, so you have to make sure your eyes, okay, straight to the needles. Okay, for example, like okay, okay. For example, this is our scale. Sorry. Okay, so this is our needle. Make sure our eyes will be exactly like this. Okay, this is our eyes, for example. Okay, straight. Okay, straight to the needle lah. Straight to the needle. Okay. So for example, you can see this one, the absorber who tend to the hold his head too far to the left while reading the position of the needle on the scale. So if you are read with this scale on the left, so maybe the reading will be wrong lah. Okay, that's why we call the observations error here. Okay, normally also come from the human lah, the observer error. Means come from the human error. Okay, so next the last error is the random error lah. So this is unknown. Okay, unknown causes. Okay, occur when all systematic error have been encountered lah. So we already study about the systematic error. On the systematic error, we have the observation error. We have the uh, what okay, instrumental error, environmental error. After we are study about this instrumental error, environmental error, observation error, so the last part is the random error lah. So this is unknown causes lah. We don't sure what what the error. Okay, so that's why we call the random error. Okay, but it's very small effect lah. Okay, it's small effect. Okay, required at the high degree of accuracy lah. So this random error can be avoided by increasing the number of reading and then use the statistical mean to obtain the best approximation of the true value. So normally we can increase the number of reading and also we can use the statistical analysis. All right. So next is the dynamic characteristics. Okay, so this one that I mentioned to you, dynamic will be measuring the varying process condition. So on the varying process condition, for example, like measure the heartbeat. So when we are running, so how our smartwatch will measure the heartbeat. So this one we call the varying process condition. Okay, so the instrument really respond instantaneously to the change in the measured variable due to such things such as a mass, thermal capacitance, fluid capacitance, and or electrical capacitance. But sometimes we have the delay delay to measure the on the dynamic. Okay, on the dynamics process, normally we have some delay. For example, like I mentioned to you, is the how the smartwatch measure the heartbeat. So it's not automatically. So the device is not respond faster. Maybe have some delay lah. Okay, some delay when we measure the dynamic response. Okay. All right. So the dynamic behavior of an instrument is determined by subjecting its primary element, sensing element, to some unknown and predetermined variation of the measured quantity lah. Okay, we have three most common variation in the measured quantity. We have the step change. Okay, we have the linear change and we have the sinusoidal change lah. All right. So for example, the step change. Okay, for example, like this one. So this is our input, and then we have. Okay, this is our step. Okay, this one we can call as the step change. Okay, for the linear. Okay, this is our output. So this we call the linear change, and then the sinusoidal. Okay, something like this. Okay, this one like our input. Our input. Okay, this one we call the step change. Okay, this one is a linear change, and then this one will be sinusoidal change. Okay, so the step change in which the primary element is subjected to the instantaneously and finite change in the measured variable. So linear change in which the primary element is following the measured variable, changing linearly with the time, all right? And then sinusoidal change in which the primary element follow the measured variable, the magnitude of which change in the accordingly with the sinusoidal function of the constant amplitude. Okay, this is definition of the step change, linear change, and sinusoidal. Okay, so on the dynamic performance characteristic of the instrument, we can measure, this is characteristic lah of the dynamic performance. One is the speed of response. Okay, the second is the dynamic error, lags, okay, fidelity. For example, like this, okay. So for example, we give a step. Okay, we give a step. Okay, this is our step input. All right. So this is our output. So for example, like this. Oops, sorry. Okay, maybe like this. Okay, this one we call the speed of response. How this is our output. Okay, this is our input lah. Okay, our input in the, we give a, for example, like step change. Okay, step change. So how our output follow to the exact value lah. That means follow the step. Okay, follow the step change. Okay, this one we call the speed of response. How this output respond to the inputs. Okay. And then the dynamic error will be different between the true and measured value lah. Okay, for example, this one this one we call the steady state error lah. Okay, that means this value. Okay, this is actually, this is expected value here. All right, this one we call the error lah, dynamic error. Okay, and then lag, that means the delay. So this one respond lah. Okay, we have the delay here. Okay. So this is some we call this characteristic of the dynamic response. Okay, so next we go for the statistical analysis. Okay, statistical analysis to separate as far as possible the true from the error by narrowing and define the region of doubt. So to make statistical method and interpretation meaningful, the large number of measurement is usually required. Okay, so this one we are studying on the statistical subject lah. So we have a data. So actually we have to get large of data lah. Okay, large number of data, then we can do the statistical analysis. Okay, for example, the statistical analysis, we can calculate the arithmetic means or the average. Okay, so for example, we have set of number of measurement. So this is average lah, the formula for calculate the arithmetic mean. Okay, for example, we have the n xn. Okay, x1 plus x2 until xn divide by n number of number of data. Okay, number of data. This one we call the arithmetic mean, or sometimes we can call average. Average value lah. Okay, deviation. Deviation is a difference between each pitch of the data and the arithmetic means. Okay, this means for data number one. Okay, this is data number one minus by average. Okay, minus by average or arithmetic means. This one we call the deviation. All right, this one we call the deviation. All right. So next, the average deviations. Okay, that means we calculate the for example, we have the 10 data measurement. So for the 10, but that means absolute D1 plus absolute D2 until the absolute D10. Okay, divide by 10 lah. This one we call average deviation lah. Average deviation. Okay. So next is the standard deviation. Okay, this is formula for standard deviation. All right. So D1 power of 2. Okay, actually S equal to square root of D1 power of 2 plus D2 power of 2 until D10 power of 2 divide by 10 minus, for example, we have 10 data. So 10 minus 1, we have 9 lah. So this we call the standard deviation. Standard deviation. Okay, so this some example. All right. So I give you another 5 minutes, okay, to try this one. First, you have to calculate the average, okay, the arithmetic means, and then calculate the deviations, okay. Calculate the average deviation and calculate the standard deviation, okay. So I give you 5 minutes to try this one, Try this one using this formula lah. First, you have to calculate the average, okay, the average or the mean arithmetic mean. So you have to this one plus, okay, divide by 10. Okay, that's the average. Okay, that's the average, and then the deviation. That means what for number 1.00 minus by average lah, minus by mean or average here. Okay, try this one. I give you try maybe just try until okay. This one we have 10. Maybe we can try until 5. Okay, until 5 measurement, only 5. First, you have to calculate the average. Okay. Okay, the average until 5 je, no need to until 10 lah. Okay, first 1.003 plus 0.998 plus 1.001 plus 1.0091 plus 0. Okay, so the average, anyone get the average?
$1.0004.
Okay, good. Okay, right. And then you can calculate the deviation. That means, for example, the measure number 1, 1.003 minus by 1.0004, for example. Okay, that is for deviation lah, for measure measure data number 1 and data number 2, data number 3, data number 4, and data number 5. Okay, that is for deviation lah. For average, okay, the average, calculate the deviation, divide by 5 lah, divide by 5. Okay, and then the standard deviation, that means square root, okay, d1 power of 2 plus d2 power of 2 plus d3 power of 2 plus until d5 power of 2 divide by n is 5, okay, minus 1 will be 4 lah. This is called the standard deviation lah. Okay, so this one you can try again, can try, so we can proceed to next. Okay, so this one you can call as the normal distribution lah. Normal distribution, sometimes we call the bell shape, or sometimes we can call as the Gaussian shape. So if you see this one, normally the lecturer see this very like this graph lah on the final exam lah, on the total coursework lah. For example, this is our A and this is maybe on the D or E. So normally student score like this at this point. Okay, at this area lah. Okay, at this area. That's why we call this is normal distribution. So if abnormal, something like this. Abnormal, okay, something like this lah. Okay, or something like this. Okay, this one is the abnormal lah. Abnormal. Okay, normally our graph like this lah. This one we call the normal distribution. Sometimes that we can call as the normal distribution, or sometimes we can call as the Gaussian curve or bell shape lah, curve. Okay, you can see this one. So this is negative error. This is positive error lah. Okay, so this is summation. Okay, so actually the random error can be positive and can be negative, but we can normally we can absolute the error lah. Will be positive, but it can be positive. Okay, for example, here it can be positive or it can be negative. Okay. Okay, so normally our distribution at this part lah that I mentioned to you. Okay, so this one you can read. Okay, that I mentioned to you. Normally our data will be here on this part lah. Okay, on this part, on the negative plus minus R here. Okay. Okay, for example, like this one, table this one, division. Okay, so total friction of the total included 0.5 lah. Okay, and then the larger data are required when the deviation may be extended to the limit to alpha or plus minus 3 alpha lah here. Okay, to here to here. All right, so that's why we need more data to be like this. Okay. Okay, so this is example. Okay, so we have two case lah, probable error of the one reading and then probable error of the mean lah. Okay, this formula, probable error of the mean. Okay, next we go for the limiting error. Okay, so the limiting error, the accuracy of measuring instrument is the guaranteed within the certain percentage of the full scale reading. Okay, for example, like manufacturer may specify the instrument to be accurate at the plus minus 2% with the full scale reflection. All right, and then for reading less than full scale, the limiting error will be increased lah. Okay, for example, like this. Okay, so this is some example. You can see this one. This is from manufacturer. Okay, given the 600 voltmeter. Okay, with accuracy with 2% plus minus 2% full scale. Okay, calculate the limiting error when the instrument is used to measure a voltage of 250 volts. Okay, that means not full scale. If full scale, the accuracy will be plus minus 2%. But this one we just only measure 250 volts. Okay. Okay, this is the solution lah. This one we have to calculate the limiting error. Okay, for example, okay, 0.02. This means this is 2% lah. 2 divided by 100. Okay, 2 divided by 100 multiplied by 6. Okay, 600. So we got 12 volts. Okay, 12 volt. This is limiting error. Okay, this 12 volt divided by 250 because we measure until 250. Okay, multiply by 100 to get the percentage lah. This one we call the limiting error. Limiting error. That means the limiting error for 250 is the 4.8. Okay, 4.8%. This one we call the limiting error. Okay, so next is the summation of error. Okay. When two or more quantity which where each of them have the limiting error combined to an equation. All right, so this combination normally involve additional, subtraction, multiplication and division operations. Okay, so the result is described in the y plus minus dy or y plus minus dy over y form. Can be assumed as an error cause a two or more reading value which have their own error combined in the worst case. Okay, for example, like this. Okay, this is a mathematical operation. Okay, for example, we have the C equals to A plus B. Okay, this is summation of error. Okay, summation of error plus minus summation of error A plus error B. All right. Okay, this is mathematical operation. If A if A minus B, so this is a summation of error lah. Similar like this one, Similar like this one. Okay, if C equal to A multiplied by B, okay, so that means plus minus percentage of A plus percentage of B. All right, so if C divided by B, all right, so the percentage of A plus percentage of B. Okay, so this is a summation of error lah. So we go for the example here. All right, so you can see this one. The certain measurement, the limiting error for voltmeter is 70. is the 2.143%, and the limiting error for the emitter is 2.813%. Okay, determine the limiting error of the power. So we know the power will be, this formula for power, P equals to VI. Okay, so the operation is multiply. Okay, the operation is multiply, and so if you see this multiply will be plus. That means the limiting error will be plus. That's why here limiting error for the power, for the voltage here, this one for the voltage, and for example this one for the current. Okay, just add. Okay, that's why the answer will be limiter of the power will be 4.956%. Okay, this is, you can see this one, the operation here. Okay, here, so just plus. Okay, because the operation will be multiplication. Okay, so the just plus the limiting error for every component. Okay, for if similar like if division, for division similar, we have to plus. Okay, for example like this one, so we know power equal to IV, V multiplied by I. This means operation of multiplication. So we have just add to, this is limiting error for voltmeter, and this is limiting error for ammeter, just plus. So this is for power, limiting error for the power lah. Okay, next, okay, this is some example lah. Okay, try this one. So you already give the answer. Try this one. Okay, the first step you have to do the limiting error. Okay, so both instrument have the accuracy of 1%. Okay, 1%. 1% lah. This one 1%, full scale is 1%. This one 100 milliwatt, also 1%. Okay. First you have to calculate the voltmeter lah. Voltmeter for and then calculate the ammeter. Try check, is it correct or not? Okay, so for example, okay, this one 1/100 multiplied by 150, 150 volt lah. Okay, so the answer is 1.5, 1.5. Okay, 1.5. Okay, this one 1/100 multiplied by 100 millivolt, milliamp, sorry, milliamp. One. Okay, this one lah. Okay, so and then from this one, okay, 1.5. Okay, 1.5 divided by 80. Okay, 80 multiplied by 100. So we got 1.875%. Okay, this one for voltage, and then for the current, 1/100 divided by 70 milliampere. So the answer is 1.429. Okay, 29. Okay. All right. So the answer will be 3.3 lah. Okay, similar like this one. The answer is 3.3. Okay. Okay, so maybe you can try this one. All right, so the current of 2 plus minus 0.01 ampere flow through the resistor of 100 plus minus 0.2. Okay, calculate the power dissipated and the limiting error. Okay, try example here. Okay, the unit of power will be like this. Okay, P equals to I power of 2 R. Okay, so that means the operation will be I multiplied by I multiplied by R. Okay. First, you have to calculate the limiting error lah. Okay. This one. Okay, this is formula lah. Okay, I mentioned to you. I multiplied by I multiplied by R. Okay, equals to, okay, you can see the operation is the multiply, so just add the limiting error here. That means 0.5 plus 0.5 plus 0.2. Okay, so the limiting error for the power will be 1.2%. Okay, that's why, okay, the answer will be 400 plus minus 1.5% lah. Okay, this is a formula. Okay, the operation lah. If the operation will be multiplied, just add the limiting error lah. For example, this limiting error for the current will be 0.5. That's why 0.5. 0.5 plus 0.5 plus 0.2 lah, 2 for the resistor. So the limiting error for the power will be 1.2% lah. Okay. Okay, for example like this. Okay, and then you have to calculate lah the percentage of okay, we get the this percentage is the limiting error. That means it's 4.8 watts. Okay, but that means 400 plus minus 4.8 watt lah. This is absolute. Okay, this is in percentage lah. Right. Okay, clear class. So maybe after that I will give your tutorials. Okay, maybe after you can try. All right. This is last. Okay. Yes, last slide. Right. So after that I will pass the tutorial 1 on the groups. Okay. Maybe you can try lah. Some example on the how to calculate the limiting error. For if you have the operation, for example, more than one operation lah. For example. Okay, so class, so next week no class for the synchronous class. So I will do a asynchronous class. Maybe I just upload my video on the YouTube, so you can watch my video lah for next week. So next week no class, no class on the Monday and Thursday because I have the Bengkel workshop for the audit for FTKEE. Okay, I'm an auditor for FTKEE. So all right, so I don't worry, I will pass the note also. Okay, note and the tutorial the tutorial. So you can try after this. Okay, all right. So because actually I have to upgrade actually my Zoom. That's why we'll be stopped at 1. I think we give a macam like I think we have less than 1 minute. So and then we'll be shut down. Okay, so that's why after that I will upgrade my Zoom lah. Okay, all right. So if no questions, okay, I will. If you have any question, you can ask in the group, also in the group. Okay, WhatsApp group. Okay, all right. So thank you very much. Okay, assalamualaikum warahmatullahi wabarakatuh.